When a single-slit diffracting aperture is illuminated by a line source of sodium yellow light, as shown here, a single-slit Fraunhofer diffraction pattern is formed in the image plane. The width of the pattern and the position of the minima are determined by the width A of the diffracting slit and the wavelength lambda of the light used. If the single slit is replaced by a screen containing two slits, each having the same width A and running parallel to each other, the diffraction pattern changes dramatically. A pattern of straight, parallel, equally spaced, bright and dark interference fringes is formed. How does this happen? Let's look at a section of the optical diagram. Each slit separately creates a single slit diffraction pattern, and both patterns are centered on the axis. This may at first seem unlikely, but remember that all rays incident on a lens parallel to the axis will be refracted to pass through the focus, so the rays passing straight through the slits will end up at the focus. These are the rays that form the centers of the patterns, so the centers of both patterns must be on the axis. It might seem that when the two patterns combine, we should simply end up with a pattern that is twice as bright. What actually happens is much more interesting. Because the two lots of light arriving at any point on the screen actually start from the same part of the same source, they are coherent. This means that when they recombine, they will interfere. All waves reaching the center of the pattern arrive in step and interfere constructively to produce a bright maximum in the middle. But for all points off the axis, one ray travels further than the other, so in some directions they will interfere constructively, and in others they will interfere destructively, depending on the actual path difference involved. Interference maxima are formed whenever the path difference is a whole number of wavelengths. The distance between the slit centers is d, so the path difference in the direction at angle theta from the axis is d sine theta. It follows that the maxima occur whenever d sine theta is equal to n lambda, where n is any integer and lambda is the wavelength. The locations of the interference maxima are thus determined by the path differences. The first bright fringe on either side of the centre is formed when the path difference between the two beams is equal to one wavelength of the light used, the next when it is two wavelengths, and so on. For a given wavelength of light, the greater the separation of the slits, the closer together the fringes are formed. Notice that in some directions the interference fringes are very weak. This can be accounted for in terms of the diffraction by the individual slits. In the directions of the minima in the single slit diffraction pattern, no light reaches the screen from either slit. So even if constructive interference should occur at these points, we see nothing. The combined result is that we get interference fringes whose brightnesses are modulated by a single slit diffraction envelope. For this pattern, the separation of the slit centers is a little more than 3 times the width of each slit. The first diffraction minimum is formed somewhere between the third and fourth interference maxima, so these fringes are very weak. This pattern uses slits of the same width, but the separation between them is increased to about 9 times the slit width. The diffraction envelope is similar, but the interference fringes are much closer together. The 9th maximum is very weak. In this example, the two slits are placed yet further apart. If you examine the pattern carefully, you can confirm that the separation between the slit centers must be in the region of 19 or 20 times the slit width, and that the slit width is much the same as in the previous examples.